Okay, let's dive into this. You know, the air all around us, it seems like just nothing, right? This chaotic, invisible stuff. But it turns out the gases that make up our world actually follow some surprisingly simple, really elegant rules. And once you know them, you can explain some pretty cool everyday things. Like this one. You ever been on a plane and noticed your bag of chips puffs up like a balloon? It's not magic, it's pure physics. And by the end of this, you'll know exactly why that happens. This is the everyday mystery we're going to solve together. So, to solve our chip bag mystery, first we need to get to know the three main players in the game for any gas: pressure, temperature, and volume. Just think of them as the three main dials that control everything a gas does. And once we figure out how they work together, we've basically cracked the code. Let's break them down real quick. Temperature, that's just how much the little gas particles are zipping and jiggling around. It's all about their energy. Pressure is the constant bombardment of all those tiny particles smacking into the sides of their container. And volume, well, that's the easy one. It's just how much space the gas is taking up. These three are always in this kind of delicate dance with each other. But to really get what's going on in that dance, we've got to zoom in. I mean, way, way in, down to the level of individual particles. This is where the real secrets are hiding, in a concept called the kinetic theory of gases. This is our first big clue. I mean, we all know how gases act, right? They're gassy. They don't have a set shape. You can squish them down into a smaller space. They push out in all directions, and they'll just spread out to fill any room you put them in. These are the things we can see, and the kinetic theory tells us why they happen. And here is the why. Gases don't have a shape because their molecules are like these tiny little loners floating super far apart from each other. They're so easy to squeeze because there's just a ton of empty space between them. And that pressure they create, that's nothing more than billions of these little particles moving at insane speeds, constantly crashing into the walls. It's like a microscopic mosh pit. Okay, so this is it. Our first huge piece of the puzzle for cracking this chip bag case. It comes from a guy named Robert Boyle, and it is all about the relationship between pressure and volume. This gets right to the heart of what's happening up there in that airplane. So Boyles' law says that if you keep the temperature steady, the volume of a gas is inversely proportional to its pressure. In plain English, they have a perfect seesaw relationship. When pressure goes up on one side, volume has to go down on the other. It's a perfect balance. Now I know this might look like something straight out of a physics textbook, but just focus on that top graph with me for a second. It shows you that seesaw effect perfectly. Just follow the line. As you move to the right and increase the pressure, you see how the volume drops? It's that beautiful, predictable, inverse relationship in action. And naturally, there's a super clean little formula for this. P1 times V1 equals P2 times V2. All that's really saying is that for any amount of gas, if you multiply its pressure by its volume, you'll always get the same number, as long as the temp stays the same. This little equation is a really powerful tool. But hold on, pressure is only half the story. What about temperature? If you've ever left a basketball outside on a freezing cold day and found it's all sad and kind of flat, you have seen our next clue in action. And this brings us to another scientist, Jacques Charles. Charles' law totally flips the script. It says that if you keep the pressure the same, the volume of a gas is directly proportional to its absolute temperature. That absolute part is important. It just means we use the Kelvin scale, the one where 0 means all particle motion literally stops. So no seesaw this time. They're more like dance partners moving together. When temperature goes up, volume goes right up with it. And check it out. This bottom graph shows that partnership perfectly. It's just a straight line, right? As you crank up the heat along the bottom, the volume climbs right up in perfect lockstep. You heat a gas, it gets bigger. You cool it down, it shrinks. Simple as that. And yup, you guessed it, there's a simple formula for this one too. V1 divided by T1 equals V2 divided by T2. This just means the ratio of volume to temperature is always going to be the same. Another awesome, powerful tool for our investigation. Okay, let's recap. We've got Boyles' law, connecting pressure and volume, and we've got Charles' law, connecting temperature and volume. We have all the pieces of the puzzle. Now it's time to put them all together and reveal the one master key that explains the whole shebang. So on one hand, we've got the seesaw. Volume goes down when pressure goes up. On the other hand, we've got the dance partners. Volume goes up when temperature goes up. The real stroke of genius was when scientists realized, hey,
we can merge these two ideas into one single powerful relationship.
And boom, there it is, the combined gas law. Forget two separate rules. This one beautiful equation tells you everything. It says that for any gas, if you take its pressure times its volume and divide all that by its temperature, you always get the same constant number. This is our master key. It lets us predict what happens when everything is changing at once, which is exactly what's happening on an airplane. And this is the final piece of our puzzle. Think about it. As the plane climbs higher, the air pressure outside the chip bag drops a lot. But the air that was sealed inside the bag is still at that higher ground level pressure. So you get this huge pressure difference. The high pressure inside pushes out against the low pressure outside, and poof, the gas inside expands and the bag puffs up. Mystery solved. So a simple, puffy bag of chips on an airplane becomes this perfect demonstration of a universal law of physics. These rules don't just apply to snacks. They govern the air in our lungs, the weather systems on our planet, even the gases burning inside distant stars. It really makes you wonder, doesn't it? What other hidden rules are all around us, just waiting to be discovered?